Here's another problem in projectile motion. It's slightly more complicated, but it's still fairly similar to the one we just did. So this is in chapter 4. So this is chapter 4. And the first thing I tend to do with these is to draw them if I don't have a picture. So here we can see that we have a volcano. Yeah, I can draw a volcano. And it has a rock that landed, sort of went up, and then we guess went up and went down. And it says it landed 1 kilometer or 1,000 meters away. And if they were launched at an angle of 40 degrees, it's not really a good 40 degree, but let's say that's 40 degrees, and then landed 900 meters below. So that's where we have, that's our 900 meters, our 1,000, we're going to set up like this. And so the next thing I want to do is say, what is it that we're trying to find? And set up a coordinate system. So we want to find their initial velocity and time of flight. All right, so we have some distances, we have an angle, but we don't have initial velocity. But we already know, if we're neglecting air resistance, that our acceleration in the y direction is given by minus g, and our acceleration in the x direction is 0. So if we start in the x direction, because that's often easier, we have x is equal to x sub 0, our initial x position, plus v0 in the x direction times t. So that's our velocity in the x direction, and it just stays the same. And we know we can set up our coordinate system to be something like this, where this is our 0. So then we can say our initial x position is 0. Our final x position is going to be this 1,000, so we have that. We don't have the time, and we don't have this. That's not very promising. Okay, so all we have right now is that. The other two we want. So this isn't very promising to start with. So let's go and see what we have over in the y direction. Again, we're looking for time and velocity, so let's look at our equations. We have y is equal to initial y plus v0 yt. And this is going to be minus 1/2 gt squared, wherever I plug this in for my acceleration. And again, I've got two unknowns, so that's not very helpful. I've got a v0y and a t. I do know that my final y is equal to 0 because that's on the ground, and my initial y I have, that's 900 meters. But maybe I can look at some other equations and they can help me out. I've got y is equal to initial y minus gt. Okay, I have g. I don't know either of these, and I don't know the time, so g is the only thing I know here. So that's worse, because when this hits the ground, you can say, hey, my final speed is 0, and that's true once it lands, but at that point, the acceleration is no longer 9.8, so we can't use that. We're not in free fall anymore. We're in collision with the Earth. So you have to look at, if we wanted a final y velocity, it would be right before it hit the Earth. Okay, so that's not very helpful. And similarly, our other equation, vy squared equals v naught y squared minus 2gy minus y0. I still have my two unknowns, these two right here. So none of these are really getting me very far, but there is a little bit of hidden information here. I do have some extra information. And that is, if I have this is my initial speed, my velocity vector is in that direction, right? And we want to know this initial velocity. I've got part of it. I know the direction, I just don't know the magnitude. And I can write my x, v naught x, as my magnitude, v naught cosine of 40 degrees, right? That's the initial velocity in the x direction. And in the y direction, I can do the same kind of thing using SOHCAHTOA, and I get this. And I know you're thinking, this didn't win me very much, because if I plug it into my x equation, I get x is equal to, keeping that 0, v naught, initial v, cosine of 40 degrees, t. I still have two unknowns. So I'm not helping us out very much, but there's something about these two unknowns. I have two unknowns in this equation, and then if I look at this very first equation and rewrite it this way, I have 0 is equal to 900, right, as my Vy, plus V naught sine of 40 degrees times t. I'm going to get rid of this line here. Minus 1/2 gt squared. Okay, now, oddly enough, I have two unknowns. I have two equations with two unknowns because I know this. I know my expression for, I know cosine of 40. I can find that. So I can actually substitute. I can solve for my time here and plug it in over here, and I can get my values. So this is when you have two equations and two unknowns, you have to do your substitution. So we need to remember a little bit of algebra. So we're going to go ahead and do that. So I've got t is equal to x over v naught cosine of 40 degrees. Okay, so I'm going to put that into my expressions here because this is just, well, this is a number with my v naught. So I'm going to throw that in over here. And it turns out I can do a little bit of a cheat. I can make this easier than it looks. I've got 900. I'm going to put my v naught sine of 40 degrees. I'm going to put my t in here. X over v naught cosine of 40 degrees. And I can substitute this t, put in a t squared here, but it turns out I don't need to because look at what happened. My initial velocities dropped out right there. And this, again, this x is 1,000, so it's known. So I can just keep it in this form. This is unusual. But this makes it a little easier to solve for. It doesn't really matter, though. But this way I can just solve for the time. So if I set this up, I get 0 is equal to 900, and this is a meter, plus sine of 40 over cosine 40 is tangent of 40. And x is our 1,000. That's this right here. 1,000 meters minus 1/2, not 4 point, sorry, I already took the 1/2, minus 1/2 times 9.8 meters per second squared, t squared. And so now I just need to find out what each of these numbers are. And if I look at my notes, this is 1,000 tan of 90. That gives me, putting all these numbers in, this becomes a 4.9 meters per second squared. I didn't write down what that's equal to, but that gives me a t, because I add these two terms together, move them to the other side, divide by 4.9, and take the square root. I know, it's a lot of algebra, but you can do it. And if you have questions, contact me, right? If you're not sure about your algebra and you didn't get the same answer, do let me know. But you should be able to get to this answer of 18.8 seconds. And from that, we can use, I think it's easiest to use this expression right here to put the time in. And so if I use that expression, I have time is equal to 1,000 meters over v naught cosine of 40 degrees. If I put in 18.8 seconds, then I'll get, and then I get v naught is equal to 1,000 meters over 18.8 seconds. The units are good. And then there's a 1 over cosine of 40 that I need to include in here. And when I do this, I get a 69.4 meters per second as the initial speed. So that's the value that you get doing this problem. You've got you find the time it is in the air, and then it needed an initial speed of about 70 meters per second. And so that tells you how fast these rocks are coming out of the lava plume, out of the volcano, and coming down and landing.